Welcome everybody to our latest series on the SMO Senior 2020. Before I start by going through the questions, I would like to highlight a few points about how the contest is conducted, as well as a few unique aspects to the SMO Senior, which are perhaps a bit different from the SMO Junior, the SMO Open, and other contests around the world. Now, in terms of the technical information, it is still 2.5 hours and 25 questions. And like the SMO Junior, out of these 25 questions, 5 are multiple choice, while the other 20 are just short answer questions. I believe I forgot to mention that the short answer questions have integer answers from 0 to 99999. So one quick way to check whether you have gone astray is if you can tell your answer is heading in a non-integer direction, at least a non-positive integer direction, you can kind of tell that something has gone wrong. However, there's something unique about the SMO Senior, which is that it focuses on a rather specific set of topics for the majority of these problems. Now, in the recent 5 to 6 years, the intention was for the SMO Senior to more closely mirror the topics which are tested at O-level equivalent, and that means that a lot of the questions usually come from the same topics. Not to say they're easy, but that there is a focus on things that are usually examined in school for students taking part in the SMO Senior as well. So you would expect that there would be only about 2 questions on number theory. There would only be about 2 questions on combinatorics. Maybe you would get 3 questions on geometry. And by geometry here, I'm excluding trigonometry. So all the remaining aspects of algebra are heavily emphasized in the remaining 18 questions. So that means that I will just largely categorize it as algebra, but algebra includes things like trigonometry, polynomials, logarithms, indices and surds. It includes quadratics, but it does not include calculus in any way. So calculus is one of the topics which is excluded from the SMO Senior. Now that means that if you have a firm grasp on most of the core topics up to an O-level equivalent, you have at least a fighting chance to tackle a majority of these questions, even if Olympiad is a little bit newer to you. Now, this is most prominent in the first 10 questions, which we will cover in this video and the next. So you will see that there's plenty of algebra and the other topics only kind of peek in towards the end of the paper. Specifically, since all of these usually appear towards the end of the paper, we can say that the questions aren't really sorted in order of difficulty necessarily. A lot of times the questions at the back are just those of a different topic. Now let's proceed into the first 5 problems, which as you will see are all algebra related in some way. For the first one, b is a positive integer, and we are told that the minimum possible value of the quadratic function 5x squared plus bx plus 506 is equal to 6. And we are asked to find the value of b. There are 2 reasonable approaches to deal with this. One of them is probably a little easier than the other computationally speaking, but given that you have ample time to deal with these questions, about 6 minutes per problem, I think either method is perfectly fine. So either you can complete the square, or you can use the discriminant. Now, since both of these methods are relatively quick, let me explain both of them. So for completing the square, that's simply because completing the square is normally how we find minimum values, so no difference here. We can complete the square, 5x squared plus bx plus 506. We first factor out 5 from the first 2 terms, and then after that, we can just complete the square as usual. x plus b over 10 squared minus b over 10 squared plus 506. And so this would simplify a little bit. 5 times of x plus b over 10 squared, and the remaining constant is 506 minus b squared over 20. Now this implies that this b squared over 20 can tell you what b is, because this portion here is equal to 6. That's the minimum value. So if we just simply solve it in the usual way, this only takes us a moment. 506 minus b squared over 20 equals to 6. So b squared over 20 equals to 500, and it is fairly clear that it would give us b equals to 100. That's option B. Now I also mentioned the discriminant because I think that's a little bit faster in terms of the computational aspect. Now the reason comes from how a quadratic graph looks like. As we know, when the coefficient of x squared is positive, the quadratic graph would look something like this. And we know that if the quadratic graph looks something like this, here we are saying the minimum value is 6. Now I shall hesitate to draw the axis because we are not quite sure what the minimum point is. We just know that the value is 6, but we don't know what's the value of x just by looking at it. The point of noticing the minimum is 6 is that it only touches it once. This is a tangent line. So that means that 5x squared plus bx plus 506 equals to 6 should only have one solution. Now if we move this 6 to the left hand side, 5x squared plus bx plus 500 equals to 0 has one solution, and that means that your discriminant is equal to 0. So discriminant is b squared minus 4 times 5 times 500 equals to 0, and once again it tells us quickly b is equal to 100. So here we have two different perspectives on the problem, and of course you could just pick either one to get the numerical answer for b. Alright, let's move on to question 2. Which of the following is equal to the square root of 5 plus square root 3 plus the square root of 5 minus square root 3? The thing that immediately catches my eye is that 5 plus square root 3 and 5 minus square root 3 are what we call conjugates of each other. Now these are conjugates of each other, and that means that if you add them, it is something nice. If you multiply them, it is also something nice, and that comes from the plus and minus. So that's what we mean by conjugates. Whenever we have an expression about conjugates, we don't really mind combining them in ways that are normally unpleasant. So namely, in this example, let's call this expression x. I'm going to just square the entire thing. Now x squared would be 5 plus square root 3 plus 2 times the product of the square roots, and then plus 5 minus square root 3. And here we get what we mentioned a moment ago, which is that you have the sum of the conjugates appearing on the left and right side, and you have the product of the conjugates appearing in the middle. Both of these are things we are fairly happy with. Specifically, the sum of the conjugates is going to be just 10. And the product in the middle can be simplified using a difference of squares. It is just 5 squared minus 3, and this is 10 plus 2 square root 22. So immediately that tells us that x is equal to d, since we want the positive square root of this number. Now, on some occasions, you can be able to simplify the individual square roots into simpler expressions. However, since all the options here are square root of something, and so on, we kind of suspect that you can't simplify them into a non-nested square root. Otherwise, the sum would also not be a nested square root anymore. So this is a more efficient approach with that in mind. Next up is question 3, and we are asked to simplify this expression with logarithms. For logarithms, we have lots of potential rules that we can use, and the main difficulty is knowing which one to use. To know which rule to use is often helpful to see is there anything special, anything suspicious, anything unique about the expressions we are asked to evaluate. Now, something that catches my eye immediately is that we have 25 and 9. Now, 25 and 9 are square numbers. There's 125 and 27, and these are cube numbers. Now, there's a useful identity which I would like to share about logarithms. And that would help us to deal with this sort of example, where you have got squares in the base and cubes in the base, and squares and cubes for 9 and 27 as well. You can use the fact that the logarithm base a to the power of n of b to the power of n is the same as just the logarithm base a of b. So, in a sense, you're cancelling off the power of n. Now, the reason why you can cancel off the nth powers is that this can be written using a change of base as log b to the n over log a to the n, which is equal to n times of log base b over n times of log base a, and after cancelling off the common factor of n, we get back to log base a of b. So this is useful in turbocharging our simplification of what's inside the parentheses, because log base 8 of 5 can stay there for now, but this reduces to log base 5 of 3, since 25 is 5 squared and 9 is 3 squared. This also reduces to log base 5 of 3, since 125 is 5 cubed and 27 is 3 cubed. So all it becomes is 3 times of log base 5 of 3. However, we know we're not done because all the desired expressions are just a single logarithm with no constant factor like 3 on the outside. Now that means that we expect further simplification, and the easiest way to induce that further simplification is to just use a change of base again. And when you're unsure what base to use, just use the regular log base 10, and that would be good enough. So you see immediately that log base 5 is going to cancel out, and log 8 is actually the log of 2 cubed. So the log of 2 cubed is 3 times of log 2. One more factor cancels out, and finally this is log base 2 of 3. Many times when we see the word simplify, there are many meanings of simplify, and in the context of a competition, the only time when they can ask you to simplify is if it is a multiple choice question, because otherwise there would be many different ways that you could conceivably simplify some expression and say that it is simpler than what you started with. So essentially, when you see simplify, it means try to make what you're given look like one of the options in the multiple choice question. And since all the multiple choice options involve a single logarithm, that should be your objective, combining the logarithms until many of them cancel out and simplify. Next up, question 4 is a rather annoying looking problem at first glance because it has fractional exponents all over the place. However, we have the slight consolation that these fractional exponents, beg your pardon, are all 1 over 101 times something. So the first thing we're going to do is to do something to make our life easier and to at least make it a little bit more pleasing to the eye. We can just take everything to the 101th power. Now if we take everything to the 101th power, then the powers become 1/5, 1/3, and 1/2. So we are left to compare them with at least a little bit more friendly looking exponents. But still, it may not be very clear just yet which of them is larger than the other, since fractional exponents do not lend themselves well to computation. So now we can raise them to a power, again, to try to reduce all the exponents into integers. However, I think we don't really want to raise it to the 30th power all at one go, for the simple reason that something like 6 to the power of 15 and 50 to the power of 6 is a slight nuisance to calculate. So perhaps we could just do it 2 by 2 instead of calculating them all at once. So we'll start with comparing the first two. The first two, we can raise it simply to the 15th power, which would make it into 50 cubed, and 10 to the power of 1/3 would become 10 to the power of 5 respectively. So these are the 15th powers, and these two are not very difficult to calculate at all. 50 cubed is 5 cubed times 10 cubed, which is 125 times 1000, while 10 to the power of 5 is just 100,000. So that immediately tells you that the first number is larger than the second number. In other words, B is less than A. So that brings us to 6 to the power of 1/2. We need to compare it to either one, and I'm just going to compare it to the first one, so the first and third this time. So I'll compare the first and third, and instead of raising to the 15th power, this time we raise it to the 10th power. So 50 to the 1/5. To the 10th power is just 50 squared, while 6 to the 1/2 to the 10th power is 6 to the power of 5. Now 50 squared is 2500. 6 to the 5 is admittedly a bit annoying, but the consolation is that this is really quite big, and this is 7776. Now what that means is that if you were calculating this one by one, and then you got 6 cubed, which is 216, multiplied by 6 squared, which is 36, it is already clear that 200 times 300 is more than this. So you don't actually need to calculate 7776, you could have just observed that it is bigger right away. This tells you that C is larger than A. And that gives us option C as our answer immediately. Finally, let's look at question 5. And we are given a strange combination of functions. There's a logarithm, there's an exponential, there's a power, and the subject is sine x. So it's all a little odd. We are just told that x is between 0 and pi over 2, which is the first quadrant. And once again, we are asked to sort them in ascending order. At first glance, such questions may look intimidating. However, you notice that sine x is the subject of all three. In other words, all the three p, q, and r can be thought of as functions evaluated at sine x. We do know that x is in the first quadrant and x could be anywhere in the first quadrant. If x could be anywhere in the first quadrant, then sine x is between 0 and 1. And it could be anything between 0 and 1, excluding the endpoints. So we could rather easily use that to compare these three expressions: log base 10 of sine x to the power of 10, and 10 to the power of sine x. Now first up, p is the logarithm of something between 0 and 1. That means that it is going to be less than log base 10 of 1, which is 0, so p is negative. Q is somewhere between 0 to the power of 10 and 1 to the power of 10, so that means that q is somewhere between 0 and 1, depending on the exact value of sine x. Finally, r, which is 10 to the power of sine x, is between 10 to the power of 0 and 10 to the power of 1, which means that r is between 10 to the power of 0, which is 1, and 10 to the power of 1, which is 10. Very nicely, this shows that p, q, and r lie in three zones which do not overlap at all. And that means we don't even need to consider different cases of sine x and to double check that the same sequence always works. Instead, we can say immediately that p is less than q, which is less than r, and that would be option A. As you can see, all these 5 problems adhere quite closely to algebraic topics which are covered up to an O-level standard, except that maybe the way the question is posed is a little bit more challenging. So in the next video, we'll be looking at questions 6 through 10, which has a similar flavor, i.e. rather heavy in algebra. So see you in the next video.